Hi everyone. In this video we're going to finally formalize a little bit of this estimation that we've been doing using rectangles. So we're just going to make this a real general case and see if we can build up a little bit about what we're doing and add even a little bit more notation. So we're going to get the sum notation involved, and we're also going to get some naming of these different techniques. Okay, so this is going to be like my generic calc2 function, y equals f of x. And we would like to approximate the area under this curve on this interval AB. So this is what we're going for. Okay, so we know that the interval goes from A to B and that we're going to use n subintervals. Again, the goal here is to be as general as possible, so this applies no matter which function we run into. We do need continuous functions for the most part, or we can get in some trouble, but otherwise this is going to do fairly well for us. Okay, so if we want to calculate the width of each subinterval, so let's say this is a subinterval, we're going to call its width delta t, because I'm calling this, oops, I didn't call it, f of t. So that's going to be the t-axis, and the width of a rectangle is going to be a little change in t, which is called a delta t. So to find delta t, it's the same thing we've done before, but we have to be general about it. We need to know how long our interval is. So our interval extends from a to b, which means its length is b minus a. So we have to cover a length of b minus a using n subintervals. So this is how you would calculate your delta t in general. Now I want to go through, and this might seem silly, but we're trying to work in some of our subscript notation to work up to the summation. So I'm going to go through and I'm going to give t names to each of the endpoints. So let's just say this is what my subintervals look like. We won't do the whole thing, but just to get us started. So I'm going to name the first one t sub 0, and we actually know the general form of the value of t sub 0. We know t sub 0 should be at a. So I'm starting at far, what is that, left-hand side? Let's see if I can rate a t. Okay, so our first endpoint of a subinterval is named t sub 0, and it happens at t equals a. If we wanted to find t sub 1, so that's going to be, you could either call it the right-hand side of the first rectangle or the left-hand side of the second one, whatever you want to say there. It doesn't just have a nice value that we've already determined, but we know that what we do is we'd say, okay, if the width of the rectangle is delta t, then we are delta t units to the right of a. And notice delta t should be positive. Our interval notation, a, b, you have to put those in ascending order, so a has to be smaller than b, which means this has to be positive. Okay, so t1 is going to happen delta t units from a. T2 is going to happen delta t units from T1, so we'll be adding 2 of these delta t's. Again, over to this picture, let's see if I have a color for you. We're saying for that second one, if we want to figure out where this is at, we know, here, let me drop it down here. We know that this distance is A. A is the x-coordinate of the very first one, the t-coordinate. We know that this is a delta t, and we know that this is a delta t. So we started at A, we've now added 2 delta t's, and this is going to continue. So our last one should be called t sub n. Okay, and let's see, if t sub 2 we needed 2 delta t's, t sub 3 we needed 3 delta t's, then for t sub n we need, oops, I'm copying from above, we need n delta t's. Okay, and we want to be a little careful about this because actually what we'd really like to see is that t sub n is the last one, so it should happen at b. We can use our formula to check and see if we successfully made that happen. So if we do n delta t's, that's like taking n times b minus a over n, and notice the n's cancel, and the a's drop out, and we really did get t sub n equals b. So don't get too freaked out by this. This is just us building up formally what these sums look like, the over and under estimates. and being a little more general, because depending on the shape of the curve, we're not necessarily going to be able to say that's an over or that's an under. It might be kind of unclear which it is. Okay, so finding a general formula. If we want an L sub n, we're going to plug in we're going to start this very first rectangle, this one right here, and we're going to say, okay, so its width is a delta t, and its height we would get by plugging in our t sub 0. And then the second rectangle, we get its height from plugging in t sub 1, and its width is delta t, and we would keep doing this. I'll run into my own stuff until we get to, and we want to be careful here, we're doing left endpoints, so we don't actually want to plug in t sub n, we want to stop at t sub n minus 1 times delta t. So what we want to do with this is crunch it up a little using that sum notation we've just been practicing. So we're going to say, okay, so this is a sum, and the typical term looks like f of something times delta t. The f never changes, the delta t never changes. All that changes is which t value we're using. So I'm going to use my subscript to indicate that. So I'm going to say we're plugging in our t sub I, and if it's a left-hand sum, we want I to start at 0 and stop at n minus 1. Okay, so this is the formal notation for a left-hand sum. Left-hand sum. And we know that the n should represent with n subintervals, number of subintervals. Okay, so I'm hoping it's not too tricky to spot what happens when we do r sub n. For r sub n, the terms are going to look the same. We're going to have f of something times delta t. What changes is just which t values. So now we're not going to want to start with t sub 0. We're going to start with t sub 1 so that we get the y value on the right-hand side. And so we're going to call these, here I'll use j. No, I don't even have to use j. We'll use I still because it means the exact same thing. Okay, so this time I'm still going to use the t values, but I'm going to start at t sub 1 and I'm going to stop at t sub n. I get to go all the way to the very last one this time. And that's a right-hand sum, also with n subintervals. Okay, and then the last one is a new one compared to when we were doing over and under estimates. Let's see if I can pick out a color that'll stand out a little bit more. Should I go back to my pink? Maybe that'll stand out. So for this one, we want to plug in the middle x value to get our height. So what we're going to actually end up doing, it's still going to be similar. We're going to take sum. We're going to take f of something times a delta t. The widths are the same. The heights are still determined by the curve, but the something is different. The something is actually, so for the first rectangle, it would be the t value directly in the middle. So we'd want the average of t sub 0 and t sub 1. So we could say something like, if we start with t sub I, we want to add t sub I to t sub I plus 1. So we want to take two consecutive t values and average them. That'll give us the midpoint. So this is the middle t value. So average the two t values on your current rectangle, plug that into your function to get the height, and then multiply by the width and add them all up. So here we want to start at I equals 0, so that on the first interval we're taking t sub 0, t sub 1, and averaging, and using that to get the height. And we want to stop at n minus 1, because then we'll be taking t sub n minus 1 plus t sub n divided by 2. So this is a midpoint rule. That might have seemed really messy, but I'll give you an example. It's really not that messy. Midpoint. And the really key thing to realize with midpoint, or you could call it midpoint sum, would be fine with me. The really key thing to realize with midpoint is that it's the middle x value that determines the height of your rectangle, not the middle y value. So midpoint rule says instead of using the left x value or the right x value, use the middle x value. and it in general will do a better job of estimating the area than left or right. What gets interesting is if you average left and right, that is actually like taking the middle y value on each interval instead of the middle x value. And that is a pretty good competitor for midpoint rule. So the average of left and right competes fairly well with midpoint rule, and we'll look at the end of this section a little bit about what determines what's going on with those two. Okay, so this is the formal notation for these. Make sure I didn't forget anything. Looks kind of scary, but we're going to keep using it, so hopefully don't get freaked out by it. The actual process of calculating a left, right, or midpoint rule is not that bad at all. So just look at this notation and really try and think about it, because it is going to keep coming up all quarter long, so we want to start getting comfortable. All right, thanks for watching.